So let's say that we trained, we validated, we test our model, and it's doing great. It has a very high F1 score, a very high precision, recall, AUC, and we want to understand why it's accurate. What is the hypothesis, the internal mechanistic explanation behind that model? We're gonna cover this in more detail around week 5 or 6 of the course, but I'll just give a little bit of an introduction to that. In the context of linear models, it's very easy to find out what the model is thinking, what is the actual biomarkers that the model is prioritizing, is identifying to do predictions, because linear additive models don't have any complex nonlinear interactions that would change the proportion of the importance of those features when you want to interpret them in terms of how important they are for the outcome. For those more complex models, there's another approach. But for linear models, when you're working with continuous outcomes, or logistic regression models, when you're working with categorical or binary outcomes, you can simply look at the model weights after you train it, or the betas, the regression betas, the regression coefficients for each one of the input features, and you can rank them from the largest value to the lowest value, and you can look at the top ones and the bottom ones, the most positive and the most negative ones. So a positive coefficient in the context of linear additive models, it means that the prediction increases as the feature increases. So in my logistic regression model, I have this feature here with a very strong positive value, or higher, the highest positive value. This means that this is a top contributor to that true outcome, that positive outcome. Let's say if you're trying to predict type 1 diabetes, and then your results look like this, then it means this feature is the top risk factor. If you see another feature with the lowest negative value when you try to predict type 1 diabetes, then this feature is the most protective biomarker. It's pushing down the probability of disease. Well, this was actually a data set that from the Collab notebook. It's not type 1 diabetes, but just to illustrate the idea. This one, if I remember correctly, was for predicting COVID severity. There are a few important things to mention, though. One thing is that this coefficient size, or model weight size, or beta size, they're only meaningful when your features are scaled. If you have one protein here, for example, in a completely different range of values versus these other proteins, then this number here will be artificial. It will not reflect a true contribution. So all the data needs to be scaled so you can rely and interpret these values. And another limitation is that this, as I mentioned before, these coefficients, they only work for linear models. So this in this interpretation will not work for nonlinear models. Like, this doesn't work with random forest, with XGBoost. We're gonna cover that in the incoming weeks. And these are just some additional references to complement the course material. They're optional, but I would recommend they're good readings to develop this foundational concepts, this foundational knowledge on this topic.